pratar alla samtidigt här. Vad ville du? Nej, jag ska... Hi. Welcome to Netnod Spring Meeting. Nice to see so many. This year, actually, we had 193 registered. So we'll see how many will actually turn up. Maybe it's a bit early yet, so. This year we turned it up a bit. And this year we have a moderator that's going to help us. And his name is Rob Allen. So he will be presenting everyone. And so if you have any questions to me or to Rob, you just grab us. I just wanted to tell you that special diet and food is by the conference, the reception here at the conference floor. And you also have the normal coffee break just outside here and also on the mezzanine floor as usual. So welcome up to the stage. Rob Allen.
Thank you. Hello, good morning. Can everyone hear me? Hear me at the back? Yeah, great. My name's Rob Allen. I'm moderating today and tomorrow the sessions at the Netnod Spring Meeting. Very happy to be doing that. For those of you that don't know me, I used to work for about 10 years at the RIPE NCC, and since 2012 I've been working as an independent communications consultant. So just a few very quick kind of housekeeping announcements before we get started with the meeting. The presentations that you'll be seeing over the next few days are all available on the Netnod website. As they're being presented, they will be mostly uploaded, so you can have those for reference and you can follow along. We're also streaming on YouTube. So if you are incognito, just be aware of that if you want to step up and ask questions. The hashtag is NetnodMeeting. Tonight, the buses will leave at 6:15 sharp for the social at the restaurant Asplund. And just one other quick announcement. Tomorrow morning, if you look at the agenda, there is 9:30. There's no coffee break at the there's a coffee break at 9:30. That will also include sandwiches and a kind of light breakfast. So something a bit more than fika, but slightly less than an English fry-up. Okay. So with that, we're going to get moving with the very first presentation. It gives me great pleasure to welcome to the stage to give the welcome and the update from Netnod, the Netnod CEO, LM Jogbäck.
Thank you very much. So, thank you very much, everybody, and thank you for being here. I think this is the most important thing for me, that is to see so many of our customers and our partners and our friends out here in the audience. I hope you will have a really good day here today. As you heard from Siri, I would like to say close to 200, but it's 193 registrations. We actually had to close the registration a slight bit early this year because it was so popular event, and I'm very happy for that. I hope you will have a good opportunity here to meet colleagues and potential partners around the industry and have a good chat, not only during the breaks of the meeting, but also in the social tonight. I also hope you will see and hear good information from 17 different great talks about all kinds of interesting subjects. And of course, which is why I'm here, and what we should start with is hear the latest news from Netnod. So the thing I'm going to talk about, I'm going to talk a little bit about DNS Node Enterprise. I'm also going to talk a little bit about our efforts to keep the clock ticking, and also about the updates we're doing on the IX space. To start off with DNS Node Enterprise. This is a service we launched last autumn, and as you're probably aware of from what we heard at the last meeting and what you maybe seen at some other meetings we have had, this is a DNS Anycast service for the enterprise market. We have been doing DNS Anycast, well, essentially since it was invented. And we started doing this for the root service, and in particular iRoot that we run. And this was a very successful way of not only increasing capacity to handle more and more queries, but also increasing capacity as one of the tools we use to battle DDoS attacks. We have also implemented that over time with our TLD customers. We run quite a lot of the TLDs, the top-level domains of the world, and we decided also to make this available for the enterprise market. This is a service that is 100% made in Sweden. We have made it ourselves. We sell it with a 100% availability, not 5 nines, 1 and 2 zeros. I'm one of the zeros. And it's something that we want people to be very, very confident about, that it always, always works. It's designed to work all the time. This is a service that we basically, okay. Technical problem. This is a service that, as said, it has TLD quality, and it's this service that we basically sell via partners. So if you are an end user, please come forward to us. Check out the webpage, kaffadns.anycast.nu, if you want to buy the service as an enterprise. If you are in the business of actually want to sell this service to your customers or as a DNS partner, don't hesitate to contact one of us, me or Miguel. Where is Miguel? He's out there. He's out there. Okay. Contact Miguel and say you're interested about this, and we will definitely help you to make a successful business. Of course, all of this is about quality, and as a lot of things that we are doing, what we try to do here is to provide rock-solid DNS. The next thing, keeping the clock ticking. We have talked, I think we started this we have done the NTP service for quite some time, and we started the next generation NTP service where we developed our own hardware, where we run the NTP service in FPGA in 2014 and launched the service in 2015, if I'm not correct. I'm looking at Patrick here. Is that good? Yeah, thanks. And what we have been doing with this service is that we actually, for the first time on a new platform, we inserted a leap second. And you think, how hard can it be? Amazingly, it's very, very complicated and hard. You will hear more information about this from one of our presenters later. But the interesting thing is that we actually managed to do this without a hitch. And it worked on all these services available, and it worked the way we planned it. And as I said, this is an amazingly difficult thing to do. The other thing we're doing with this, we're doing continuous development for the hardware-based NTP service. Today, that is mostly about doing bug fixes and stuff like that. We have done some interesting bugs that we have fixed. One of these is that we actually respond to ping and trace route from the NTP service. It's something that you don't really think of from the beginning, that you have to sort of implement all the stuff again from the start. Another thing that we have done, which is closely to this, is we started to sell frequency and time as a service. So we sell P2P connections to our cesium clocks to various providers and various customers that are in the need to have both a very accurate reference frequency signal, but also have the official Swedish time on a contract and be able to use that in their service. And as we like to frame this is rock solid NTP. And I hope you start to see a theme here of what we're doing. The last thing I'm going to talk a little bit about, that's the Netnod IX. Netnod IX is sort of the flagship of our product. It's the biggest service we run, and it's a very important service to keep the internet working in this region of the world up in Scandinavia. And we have been doing this since we started in 1996, and we continue to do it over time. What we have been doing and continuously doing now this spring is that we're doing a rebuild of Netnod IX Copenhagen. We are also rebranding the Netnod IX. It used to be called Comics. We are sunsetting that name, so this will be Netnod IX Copenhagen. Despite the name, we actually will still be present in Malmö, and Malmö is going to be part of the Netnod IX Copenhagen, but we will market this and use this in communication for a name for the exchange point. This rebuild makes it possible for us to provide a redundant port in Copenhagen. Okay. This thing is not really, I'm not a pop star. So we are going to provide a redundant port in Copenhagen. We think it's very, very important that we have a stable, secure, and fully functional IX services, and that we can continue to provide a rock-solid IX. So the redundancy and stability is very important for us in this space. However, we know also that a lot of customers is using their own means of getting redundancy for exchange points, and not only relying on one exchange point, and maybe sharing the load between sharing the load between Stockholm and Copenhagen, sharing the load between Copenhagen and Amsterdam or London or whatever. So we're still going to provide a single port of the IX in Copenhagen, and so we will have both the redundant port and the single port in the exchange point in Copenhagen. We will also start providing the single port in Stockholm. So we will also start selling only one port as opposed to the redundant port that we do today in the Stockholm exchange point. And this is also in the rebuild. We are going to use the same architecture we will be doing in Copenhagen for building the Stockholm exchange point. The other thing, and the last big event we are doing, is we are also moving away to a new service where we're going to provide an optical IX in Stockholm and Copenhagen, where we will not only provide access to shared media, but also on a very cost-efficient base, provide point-to-point interconnection in Stockholm and Copenhagen, both on a pure optical level as a spectrum or alien wavelength, but also as a gray service on 10 gig and 100 gig with a transponder-based solution. This, of course, recalls an update of the prices that we're doing. We are changing the prices from the 1st of July in both Copenhagen and Stockholm. That means that existing contract that has a contract date on or after 1st of July will get the new prices, and new contract entered into after 1st of July will get these new prices. And the prices will be slightly lower on the redundant port, the same price as the previous single port in Copenhagen for a single port both in Stockholm and Copenhagen, and the same prices for a single and redundant that we have been used previously in both Stockholm and Copenhagen. So we'll have the same prices as Stockholm and Copenhagen going forward. Another thing we're also doing with the prices is that we want people to utilize this and feel that they can get a good value out of the system. And that means that on the highest possible speed that we sell on the exchange point, which currently is 100 gig, we will get a 40% discount on additional ports going forward on this. That means that when we launch 400 gig or 1T as a port, this is the discount we'll get on the second port of those speeds. But for currently, this is for 100 gig moving forward. When it comes to the optical exchange point, this is the prices we're going to start selling with that. And as I said, we're introducing this in Q3 in Copenhagen, where we have 276,000 per year for 100 gig point-to-point gray lighting. And we have a 10 gig point-to-point for 24,000 a year in these both metros. And all of these are prices that is on net. So that means that it's on the locations, on the data centers, where we have an on-net presence. We will be able to build on customer request and on-net presence in your premises at home. And we will have that as an on-request price, depending on what the cost will be to actually get the fiber infrastructure in there and get the nodes installed and everything. We also, as I said before, we will sell alien wavelengths as well. We are not having a price for that yet, but that is something that will come as well. So what that means is that Netnod want to be the one-stop shop for all your interconnect needs, any style, regardless if it's a redundant connection to the IX or a non-redundant connection to the IX on L2, if it's a private VLAN on the IX for doing transit or doing private peering over the L2 infrastructure, if it's a lit point-to-point service on L1, or if it's a layer 0 point-to-point optical spectrum. And we want to take the interconnection service into the next level. The last news here is that we are also, as we had a cooperation previously with NICS, we're also officially launching Netnod Oslo, which is powered by NICS. It's still the NICS exchange point. We're doing this in very close cooperation with the NICS team. And what it means that is Netnod is going to be the one-stop shop for IX in Scandinavia, where you can get exchange points in both Stockholm, Copenhagen, and Oslo on the same contract with the same support contact going forward. It will still be run by the NICS team. You will hear more what has happened with NICS from Kjetil tomorrow. And, but this is an opportunity, especially for telcos not present in Sweden or Norway, to get a one contact for all the exchange point needs. So with that, I'm done today. I hope you will have a really, really good meeting today. Tune in tomorrow morning. You will hear the technical updates on the Netnod IX and the single port and how it's achieved and everything from Matthias. And you will hear Kjetil talk about the NICS update tomorrow morning as well. Enjoy the talks today. As Siri said, the buses leave here for the social tonight at 6:15. Be there, please. And all in all, be fun. Thank you very much. I also want to thank our great sponsors who help us organize this event and hopefully make it a very good success. Thank you very much for the interaction. Thank you to NTT, and thank you to Portlane. I hope you will have a good meeting. And now I will hand over to Rob.
Thank you. Thank you, LM. So, the first speaker of the day is Stephen Strowes from the RIPE NCC. Stephen is a systems architect on the research and development team at the RIPE NCC, and previously he ran the IPv6 program at Yahoo. He studies network protocols and how they are used in the wild. And today he's going to be talking about network time, the NTP pool, and the 2016 leap second, which LM mentioned a little bit in his opening presentation. So if we're ready with the mic.
I think we are.
Yeah. Then Stephen, the floor is yours. Welcome.
Awesome. Thank you.
Thank you.
So usefully for a talk about time, we're running early, which is perfect. Does that mean I get extra time? Yes, so thank you for the intro. I'm Steve. I'm at the NCC. I only recently joined the NCC. And I don't usually look at time and NTP and those kind of things, but we had a leap second recently. So we have some measurements, and I pulled some data, and so we had a look to see what happens in the NTP pool. In this talk, I'm going to give some background on time and how time works and how we standardize time and how we get to this point where we care about leap seconds. I will look at the most recent leap second right at the very tail end of 2016 and what the NTP pool did with that. I'll cover some of the measurements that we have that have data that you can go and pull, and some solutions. And I should say that I have no affiliation with Netnod, but it sounds like using their NTP services might be a good thing. I have no measurement data on Netnod's NTP services. So let's talk about time. with the caveat that I'm not a physicist, so I'm talking about time mostly from the perspective of how we deal with time as networks and systems people. So step 0 is that time is really difficult to get right. Like, time in terms of how we want to use time on our systems is tough, because what we want is lots of individual independent clocks running independently that approximate some moment in time, some agreement on what time is. Whereas people tend to think about things causally, right? Event A happens before event B. Event A prime happens before event B, but we don't necessarily care about where events A and A prime happened. So coordinating time is hard, but understanding the passage of time in the universal sense is also hard. So we kind of start off from this point of astronomical time, the basis of which is where the sun is in the sky. That's our primary motivation for caring about time. And we have other notions of atomic time that measure very strictly the passage of time. And these two things sort of combine into time standards that we use. You will have heard of the ITU. There are lots of other bodies that work on time standardization. I don't pretend to have a good head for how all of those organizations interact and work with each other. But they publish time standards that represent notional definitions of how time should be interpreted. One of those is TAI. Some of these acronyms will become more familiar as we go on. TAI is International Atomic Time. That's measured by multiple atomic clocks distributed around the planet. That gives us a strict sense of how long a second is. We have solar time, which is UT1, which is, that's more notionally where the sun is in the sky. That starts to measure how quickly the planet rotates. And we're not using the sun for that. We use lots of different metrics, including some very distant quasars, to determine how quickly the planet is rotating. Because the speed that the planet rotates at is not constant. And then we have UTC, which is an approximation of UT1. In UTC, the seconds are of finite length, different from UT1. And the seconds are of precisely the same length as in TAI. And once solar time drifts far enough away from UTC, that's when we insert leap seconds to bring UTC back in line with solar time. Hence, leap seconds exist to keep us in check with where the sun is. A lot of this is kind of okay so far. Like, I'll come back to UTC in one moment, but we have lots of pain points when it comes to time and calendars that are explicitly not included in the leap second discussion. Things like summertime and non-summertime. Things like leap years. Like, these are difficult things to get right, and I recommend never ever trying to write code that deals with dates. But dates and human representations of time are different with UTC. Leap seconds mess with UTC because UTC is discontinuous. Now, seconds matter. This is a fun map. I insert this as a sort of a novelty. This is a time gun map of Edinburgh from the 1860s. We've cared about time since the mid-19th century to the second level granularity. Now, this is a military-style map where you have a military gun that fires at a known location at a known time every single day. And if you know where you are on the map, you can count the number of seconds behind the clock, the gun that you are, and determine to a second level granularity what the accurate time is. This is for military precision timing. This is in the 19th century. This is long before we got to the point of starting to standardize things like UTC and we had any notion of atomic clocks. But for the insertion of leap seconds, that is announced by a shadowy group of people called the International Earth Rotation and Reference Systems Service, which is a catchy title. And they release these bulletins that you can always get at this URL. The most recent bulletin is always there. You can get the archive of all of them. And they release these Baroque text-based documents that are not totally machine-readable. And they tell us stuff about whether there will or will not be a leap second inserted. Because we can't predict how fast the planet will rotate, we can't predict whether there will be a leap second in any particular year. The only thing that they guarantee is that there will be there will not be a leap second until they tell you there will be a leap second. Which is great. They have some sort of cadence around this. They tend to insert leap seconds either at the end of June or at the end of December. They also say that maybe we will do it in March or September, but they've never done March or September so far. Now, I'm not saying that these people are Time Lords, but I'm just saying that we're not necessarily sure which part of Gallifrey they're actually from. Like, these people meddle with the time stream. But that gets us to a point where we can start to think about standards as we think about them, like the Network Time Protocol and POSIX or the single Unix standard, and how they deal with leap seconds, because they deal with leap seconds differently, because it would be too easy if it was all the same. What NTP does with leap seconds, like if we assume for a second that NTP servers are aware of a leap second coming up, then what NTP does is it stops the clock. Now, kudos to Netnod for running a NTP service that handled the leap second, because lots of stuff that's out there in the wild doesn't necessarily do this. But a properly functioning NTP service will stop time for a second and continue. I say effectively halts the clock. I think what NTP implementations actually do is increment the clock by some sub-second value for each request that comes in during the leap second, so that you still wind up with a notional aspect of causality. Event A happened after event Z or whatever. So you get a time stream that looks kind of like this. Now this is NTP relative to atomic time, because time is always relative to something. Oops. And that's kind of okay. Like, time stops, but doesn't go backwards. What NTP also does is, in responses to NTP queries, NTP will set a flag if there is a leap second on the horizon. If there's a leap second coming up, it will set a leap indicator. And the purpose there is to tell other NTP servers that the leap second is on the way, and to tell hosts that the leap second is on the way. NTP doesn't tell the hosts what to do with that information. Its job ends at informing the host that a leap second is coming up. So what POSIX does is somewhat analogous to UTC. It jumps the clock. In the POSIX world, all days are 86,400 seconds long. And POSIX deliberately forgets the notion of leap seconds. So if you care about second-level granularity going back before the last leap second, then you need to also be looking up a table of when the leap seconds occurred so that you get precise timings. But because POSIX steps the clock backwards, the time stream starts to look like this, where you have time going in the wrong direction. This is unintuitive because people expect that time generally goes in one direction, not the opposite direction. So we wind up with this difference between what POSIX says and what NTP says, and fundamentally we wind up with something that is unexpected. Like, people don't expect time to go backwards. And because of that, things go wrong, because we are humans typing things into keyboards, and we make these assumptions. If I'm writing code today that I expect to last no longer than today, I'm not going to write code that will deal with leap seconds. But if that code escapes and is used when the next leap second rolls through, then it could break in interesting and fun ways. We generally don't assume that a leap second is going to happen, and because they are relatively rare and unpredictable, we don't usually test for them, because people tend to test for the things that have broken in the past and have scarred them badly. We have some there are real examples out there of things that break, and break in real ways. The infamous one, I guess, is the kernel bug, which was a particular printk call that, if called during that second after which the POSIX clock had been stepped back, could lead to a kernel panic. Kernel panics are not what you want. In the most recent leap second, Cloudflare did glitch, and they were dropping some small percentage of DNS queries for 6 or 7 hours because they made an assumption about time. And their recursive DNS service that was implemented in Go was willing to give them the system time as it was represented on the host, and that time was suddenly in the past, and their checks didn't catch times that were negative. So they started dropping up to about 2% of different types of DNS queries for a few hours. DNS caching probably saved a lot of things at that point in time, but 1 to 2% of Cloudflare's DNS traffic is probably a non-trivial number of DNS queries. If you're paid to read Cisco documents, and I'm not paid to read Cisco documents, but if you're paid to read Cisco documents, then they have a bunch of stuff in there on what their routing platforms do today. And it's really interesting when you start digging. Like, of course, a lot of stuff runs just fine and doesn't break, but they have lots of corner cases, including routing platforms that will simply ignore the leap second and do nothing. Routing platforms that will see the leap second and implement it twice, inserting 2 seconds. Routers that will see the leap second and crash and reboot and bring themselves back up. These are wonderful things that you want running on your network, right? This is kind of the reality of what happens when a leap second rolls through. There are a million others that you can go and find out about. So at the NCC, we do measurements. We have a bunch of measurements. We have the RIPE Atlas platform that I'm assuming most of you are familiar with. The most common probe that we have out there is the little white hockey puck-sized probe that people can stick into the back of their home router. One of the measurements that these probes do is NTP measurements. You can get the probes to send NTP queries to any given NTP service and read the results that come back out of that. Now, measuring time in a sensible way is hard because clocks drift, and home routers or ISPs may often block NTP in home networks or whatever. Like, lots of stuff happens here. We have a useful analysis at that URL on what NTP looks like from the perspective of our smaller probes, and how we try and handle the cases where NTP is blocked. But we also have Atlas anchors that are the hosted managed services, like the rack-mounted things that people will put into their data centers and colos. Like those ones, because we want a clear network, they can almost always talk NTP. And because they are real hardware and not a little box that you plug into the back of a router and hope exists and stays alive, they tend to have fairly stable clocks. So we have a bunch of measurements that, if you really want to, you can go and download. We are measuring the NTP pool over IPv6, and we are measuring the NTP pool over the other protocol that shall not be named. And these results are all out there, and you can go and you can download snapshots of this data, and it's bundled into JSON, and you can fool around with it if you like. But in terms of like the high level of what some of the data looks like, if I go back to the leap indicators, so the NTP standard has the leap indicator, and the leap indicator as specified in the RFC says that if the leap indicator is set, then there will be a leap second inserted at the end of the month. Right? Your host is supposed to remember this and do something at the end of the month. Most of the NTP servers in the pool are setting the flag on the final day. This is December 30th, 31st, and January 1st, coming into 2017. Most servers set the flag on December 31st only. And that's fair because older NTP RFCs said that if you see a flag, you insert a leap second at the end of the day, which has no bearing on what any time standard said anywhere else. So setting for the final 24 hours is fine. The fun part is that some of the servers in the pool keep indicating the leap second once we get into January 1st, even if they've adjusted for the leap second themselves. This is the sort of noise that you kind of expect to happen in the NTP pool. Looking at that another way, in terms of each of the servers that we measure during that window, we get to a point just before the clock switches over where we have up to about 80 to 90% of the servers that we measured in the pool indicating that a leap second is coming up. If you're running 1 or 2 machines, that's probably okay. Maybe you don't care. If you're running an infrastructure where you like time to be in alignment, and you have configured your machines to use the NTP pool, then you have a chance that you have some machines that have synchronized on NTP servers in the pool that aren't advertising the leap second, and some that are. And so your infrastructure's response to the NTP leap second might differ, which is probably going to make your life really exciting on December 31st when you don't want to be on call. In terms of what the leap second kind of looks like, in a sense, if I plot a time series across the leap second and just take all of the offsets that we measured. Now, some additional context here. The anchors don't step time. We tell NTPD to not step time backwards when the leap second comes through because we don't want the discontinuity. We do a lot of measurements. We like time to go forwards. So the servers are able to see the leap second, and then what we actually see is the time it takes for them to readjust back into UTC based on what NTP is now telling them. And we get this noise. And some of these are outliers because the anchor has probably lost its association with an NTP server. But we get this sort of chaotic mess as all of our hosts are trying to readjust back into what the new normal is. If I tidy that up a bit and look at particular NTP servers, particular anchors, then that's a cleaner look at what the response is like for NTPD with these particular flags when a leap second rolls through. And it's kind of fun because you get to see where it fishtails and overestimates and then has to go back. But fundamentally, these start to hit realignment around about 18 hours after the leap second happened. Kind of interesting, kind of fun. Solutions. A solution might be to use Netnod's NTP service. I don't know. A solution is to not use the pool. Can we get rid of leap seconds? That's an ongoing discussion in the ITU. It's really interesting if you're interested in arcane bureaucratic discussions. You can go find documents where they talk about the process that they're going through, and I assume that they're inviting input and opinions and experiences, but they are aware that leap seconds cause a lot of problems and cause a lot of things to break. And given how widespread technology is now compared to when these things were defined, this is a big deal. They're not going to be making a decision before 2023. But that's okay, because these sort of standards will live for decades to follow. Ignoring the leap second is an approach. Our anchors are using NTPD with some magic flags that say, just don't jump the clock. OpenNTPD explicitly ignores the leap indicator, and that keeps their code simple, and that's fine by me. Smearing a leap second is an approach that is finding consensus amongst cloud providers, where you make your users aware of what's going to happen, of course, but you have your NTP services stretch or shrink seconds such that the adjustments are much smaller, and you stretch or shrink a second for around about 24 hours around the leap second. Importantly, during the smeared leap second, your servers are explicitly not advertising UTC, but maybe that's okay compared to kernel panics and 18 hours to realign your clocks with NTP or whatever your configuration leads to. But Google's public time servers do precisely what they advertised. They said that they would start smearing the second at 2 p.m. On December 31st, and they would end the smear at 10 a.m. the following day. That's precisely what they did. That's precisely what they measured. The trick here is that you don't need to care about NTPD's implementation or settings. The NTP servers see the NTP clients see a server whose time is off by a little bit, and it can adjust without overestimating or having to jump too far. These are actually fairly tidy if you're willing to accept that. In conclusion, don't use the NTP pool. Time is really hard. Knowing what your hosts or your routers or whatever other devices are on your network are going to do at the leap second is probably a good thing. You're okay in the sense that there is no leap second coming up at the end of June. So you have until December, maybe. Or maybe it's June 2018, we don't know. It's the cabal of Time Lords who will tell us. Or you look at other mechanisms, like if you're running stuff inside cloud infrastructure, then smearing the second is definitely a way that they seem to be wanting to go. But fundamentally, all of these approaches are trying to find a way to not have time go backwards. We're looking for mechanisms to keep time continuous, stepping forward, having it be reasonably stable, and for things to not die in a fire. And that's me. That's some stuff on ATP leap seconds and what we do with that. So I'm happy to field questions. And
We do have some time, so if there are any questions for Stephen?
or opinions, or if I made anybody really mad about time.
So I'm interested in this leap smear that you were
Yes.
talking about. For that sort of period, you are out of sync with UTC. Have there been any kind of studies published on the implications of that?
Not that I've seen.
Okay.
The consensus around leap smearing, at least, is that yes, you're out of sync with UTC, but that is somewhat preferable to the other options.
Right.
Now, I should say, like, this is all chaos and doom and so forth, but a correctly working system that has a reliable NTP service that is advertising the leap second and responds correctly to it will jump time around about the leap second, and everything will be back in sync within half a second or thereabouts. And that's all fine. But experience says that that's not necessarily how things will always go. So the approach there is simply avoid the leap indicator, avoid those untested code paths. Now that sounds pretty sane, but I haven't seen any studies on like anybody who's running non-trivial stuff inside cloud providers, which is a lot of people, will be using this today. I haven't heard anybody screaming about it.
Okay.
But I haven't seen any solid studies on who's using it or how it's been. That said, Google's been doing this for a few years now. The other cloud providers are sort of falling in line. They're finding consensus on the time period that they want to run the smeared second for. And I think that the other cloud providers have normalized around a length of day. And now Google is trying to say, hey, we would like to standardize this. So I think that's fine.
Okay. Question over here, Patrick.
Much better. Thank you very much. Patrick Feltz from Netnod. Thank you for this presentation. Great stuff. Cool. Leap seconds are hard.
Yes, they are. Yeah.
But mostly just because of various bugs in definitions, as you were saying. So if it is the case that people are diving into this leap second thing, be careful and separate when we are thinking about the number of seconds since a certain point in time, which for NTP is 1900, and for the POSIX scale, 1970.
Yes.
And when you're looking at date conversion from number of seconds to time, to dates and hour and month and hours and seconds and whatever it is. One of the biggest problems is, of course, as you said, the definition of POSIX, which is just completely broken, which actually includes leap seconds in the day of the leap second, but not sort of the next day.
Right.
So you will have 2 seconds, which actually have the same number of seconds since the epoch. There is also, just in addition to your talk, there is some discussion on changing the POSIX standard, but of course, no one really wants to do that either.
Right.
So we'll see where we are.
Yeah.
Yeah, this is just a pain.
Yes. Yes. Agreed.
Any more questions for Stephen? Nope. Okay.
Well, thank you very much.
Thank you very much, Stephen. Stephen, you're going to get a little present. So just to explain what's happening here, speakers will be getting a wonderful gift and a hug at the end of their presentations. And it's a special security-conscious backpack by, what is it now again? Is it Buddy?
Yeah, it's called Bobby.
Bobby. It's a Bobby backpack. It's anti-theft. It's an anti-theft backpack because Netnod takes security seriously. There you go. Appropriately enough, having talked about time, we find ourselves almost 15 minutes ahead of schedule, quite phenomenally enough. The coffee break is scheduled to take place at 10:30. Is it already set up outside? We do. So I would propose that we adjourn for coffee, a slightly longer coffee break than planned, and we meet back here at 11 o'clock. Thank you very much.